mathematics of a very abstract character that you would think has nothing whatever to do with computation. But the constructive point of view is what makes it possible to do this very beautiful development that Dan will be showing you of, and is in the hot book, you'll see, of this kind of branch of mathematics. Constructivity is at the core. So this is partly where, in my mind, you know, I may have said this to you before, computer science is the master discipline. Okay? Math arises from computing. Okay? You start with the notion of algorithm. The notion of algorithm is a step-by-step procedure. That is the notion of a proof, which is also the notion of a construction of something, like in geometry. And it's on that basis that you build up the edifice of mathematics, but it all comes down to the idea of algorithm. So this is Brouwer's brilliant insights in the 1930s, okay, was to build that up. I firmly believe in that perspective. So it's all computer science, actually. Okay? So rather than computer science being some corner of applied math, maybe, it's the other way around. Math is actually some corner of computer science. Okay? So that's the way I like to think about it. That's my biased perspective. Okay, so now let's do something here. Okay, so so I wanted to discharge my previous obligation to you, which I mentioned, which was to say to you that that constructivity was central to all of this. The whole thing can't work if you don't have a constructive, if you're not working in a constructive framework. So this is another reason why type theory is of central importance. I can't do this on the basis of first order logic or set theory. There's no way to do this, okay? It has baked in too many bad assumptions at the from the get-go, and now there's no way out. You're down a cul-de-sac, okay? Type theory has got the right starting point because it's based on computation, and it allows us now to develop very beautiful structures, and that's what I'm trying to do. Okay, so let's look at how we do a proof of functoriality. So what I want to get at is it's a theorem, which means it's a consequence of the principle of path induction. Okay, so how do we do this proof? So I have to obscure my own work there, so let's restate it. So what I say is that...
So it seems that in the way that the path induction is stated here, the third line, which you're calling the inductive.
Yeah, I didn't know what else to call it.
Yeah. Doesn't depend at all on the second line, and it doesn't involve.
No, that's right. Yes, that's true. Because the inductive step is going to say, by virtue of the inductive step, whatever particular path you pick, it will hold for it.
Say that. So actually, you get all paths having that property.
Yeah. So you could write it like this. So here's another way that people read it. I might have written it this way last time, is rather than factor this in, what you do is you say, given any z, which is between any path in A, then J of z here is a proof of ABZ. That's another way of saying it. It's the same, but it's another way of saying it. So you're right. And then sometimes you can even just miss that out and implicitly, or think of it as a function of z, okay? And then it looks like that. So that's another way to write it. But that's the same with the principle of mathematical induction. I mean, it's just a question of like how you push around the information, you know. Okay. So now I want to do this path induction. I want to do this very simple proof by path induction, which tells you that everything in sight respects paths. So I say if f is a function from A to B, and I have a path between A and B in A, then I have a path which we will call app FA is a path between f of A, the zero cell application, and f of B. Okay, that's the simplest preservation property or respect for equality or functoriality property that I can think of. So to do this as a first example. So in other words, what I really mean is then there exists a mapping app which has the property that app FA is a path between f of A and f of B. That's what I mean when I write that, okay? So I'm going to define it. So what I'm going to do is the proof, so this will be kind of our theorem, And the proof will be by path induction on P. Now, just like any inductive argument you've ever done in your life, okay, 90% of the battle is knowing what is the inductive hypothesis that you're going to be doing. What is the motive for the induction? Once you figure that out, the rest takes care of itself. But finding that can be arbitrarily complicated, okay? Who knows, okay? There are lots of computer software that have been written to guess inductive hypotheses, and you've developed a lot of tricks. But in the end, you know, with a fresh problem, you have to think it up. So there's no magic here. I just happen to know the answer, okay? So what is the motive? So once I say the motive, then it's all easy. So I have to say what the motive is. Well, you can get, in this case, it's so simple that you can kind of figure out what the motive must be, okay? So the idea is I want to wind up proving that there's an inhabitant of this type, okay? So this is my, think of this as PAB for some choice of P. That's my motive, okay? Because I'm going to prove something about a path, little p, okay, that's supposed to be a capital P, okay? Try to make it look capital, okay? So that's capital P. So if I'm trying to prove something about a path, okay, and the thing I'm going to state about it involves, it doesn't actually involve P, but it does involve its endpoints. So it's kind of a restricted case, okay? That is, I'm only interested in the endpoint. Because the only, in other words, if you look on the left at the hypotheses, the only thing that appears in the conclusion are the endpoints of the path and not the path itself, as it happens. There are other proofs where you care about P, but in this case I don't. Okay, so that's my capital P. So you think, okay, so what is the motive going to be? Well, it's going to be, given x in A and given y in A, what I want capital P to be is I want P of xy, let me write down what it is. I want P of xy to be the following type. That f of x is equal in B to f of y in U. That's my motive. Okay, I know that this is going to work. Why? Because look at the conclusion of path induction. It says blah, blah, blah. Under whatever sufficient condition we get, we're going to be able to conclude here at step 3 that P holds of A and B. So if I plug in A and B here, I will get f of A equals B, f of B. That is, we think of it as being true, but being true means that there is actually a path in here, which I will call app-FA. Okay, so you have to always remember that in type theory, you know, when you're writing down any statement, any proposition, it's really a type. And when you say that it's true, you're really talking about it being inhabited. And generally, we're not interested merely in whether something is inhabited, but we're interested in knowing what its inhabitants are. Okay? So it's a very rich, much richer form of reasoning. Go ahead.
Isn't f of x equals f of b always a type?
What's that again? Sorry?
Isn't it always a type?
Is it always a type? What do you mean by that?
Well, you have colon u there, so you're claiming...
Yeah, what I'm claiming is I'm going to define my P to be this type. There it is. Okay? Which means that depending on where A and B live, they're in some universe. Remember the convention of universe polymorphism. So A and B are types, so it's in some universe. The universe is closed under formation of identity types, path types, so that will also be in U. So here's a particular type that inhabits U. And that's because of the closure principles of universes, okay? So that's what's going on there. That's the trick about using universes, yeah.
Why you're not making the proof for A and B true free?
Why am I what?
The proof for A and B are equal. Why you're not making it free in this proposition?
Well, it just happens to be the theorem I'm proving. If you just look at it in terms of inhabitation, I'm saying if A is equal to B, then f of A is equal to f of B. And I don't, the statement in question that I'm proving doesn't happen to say anything about P. But the proof will. The proof says, this should have said app-FP, right? So maybe that's what confused you, right? I wrote the wrong thing down there. Okay, I messed that up. Sorry about that. In other words, it's the action on paths of F and apply it to P. Sorry, I wrote the wrong thing. Yep.
So, from topic type theory, are you really talking about the universe?
Am I talking about what?
The U, are you talking about the universe or total spaces?
I didn't hear that second word. Am I talking about the what?
Spaces are universal. When you are writing a U.
Yeah, U, that's a universe, right? That's what I mean by that. And spaces inhabit, types inhabit universes. That's what we talked about earlier this week. Okay? Because it's just technically convenient to say the way you present a type is as an inhabitant of a universe. There's a reason coming up, which I'll get to, I hope I will get to by the end of this lecture. Okay, so that's the motive, okay? And what is the sufficiency? What is it that I have to show? It suffices to show. It suffices to show that given any x in A, there exists an inhabitant of the motive instantiated for xx in REFL, which is that f of x equals b f of x. Yes? I need to find something in here. If I have that, then my app fp is by definition going to be j. Let me not write out the motive. I'll just write j. X dot whatever I write down here apply to p. Okay? All right, so what do I do here? Well, this is an instance of reflexivity. So this is reflexivity at f of x, in b, excuse me, of f of x. That's a proof of that fact. So the thing I write here is REFL b f of x, and I'm done. Moreover, there's an app such to this. I can write such that if we take app and we make it act on the identity path, or reflexivity, let's call it reflexivity, on A, that's definitionally equal to, and we need to know this, this is definitionally equal to reflexivity in B on f of A. So you say a lot when you're proving a theorem. And why is that part true? Because if you calculate, take J here, which is x dot REFL in B of f of x, and if you run that on REFL, the null path in A, then the definitional equality for J says that this is REFL of B of f of A. By the obscured board, no, by this rule here, by this definitional equation right there. So the beauty of all of this is that the theorems are so much richer, right? I don't just say the flabby thing. Oh, if A is equal to B, then f of A equals f of B. Instead, I have this idea that says, no, a path in the space A can be transformed into a path in the space B in such a way that if you take the null path in the space A, you will get the null path in the space B. It won't go anywhere else. Because in principle, if I don't say this, then you don't know what path, what is the proof. See, without saying this, I don't know. For all you know, I take the self loop in A, and app-f maps that over to a loop for sure, but for all you know, not REFL. This is some other app-fp. And the question is that equal to, if this is REFL, so let's call this REFL, then the question is that REFL? Is it actually the self loop or is it some other loop? Well, the theorem is telling us, when fully stated, the theorem is telling us that it's going to preserve the null path. Okay, so that's good. Okay, and then we're done. So this is like a simple example. I'm going to do another one of a very similar character momentarily. But this is a simple example of proof-relevant mathematics, right? That we are writing out, theorems, in this case about equality, and we're thinking of them really as mappings on data structures. Because the proofs of equality are relevant and are the subject of our discourse. That's what we're interested in saying things about.
Why did we care that REFL mapped to REFL? Is it just for functoriality, or did we care?
Yeah, well, yes, essentially. And I'm not going to prove it for you, but you can prove as a theorem that app itself acts functorially in P. So it will preserve up to equality some composition and inverses. And for that, you need this as a starting fact. Because what you're going to do is, suppose I want to prove that app_f of P inverse is app_f P inverse. See, I'd like to say, for example, I'd like to know that if I start with a path, we think of it as going from left to right, and I map it over via f, sends that over to some other path going from left to right. I would like to know that if I start with the path which is the inverse of that, I would like to know that what I get is the inverse of that. Okay? Well, how do you do it? You prove it by path induction. What you do is you say, well, here's an arbitrary path, okay, P, and we look at the effect of app_f P inverse, and we say, well, by path induction on P, it's enough to consider Reffel inverse. Reffel inverse is definitionally equal to Reffel. Therefore, app of that, by this fact, preserves reflexivity. And so therefore, I can conclude that if I take the inverse path and map it by f, I will get the inverse of the mapping of the path by f. You see? Etc. Now, I want to show that it preserves composition. I'm not going to do this now. But you can guess how I would do it. I'm going to say, well, if you give me the concatenation of two paths and I map them over, how do I know that f of the concatenation of two paths is the concatenation of f of the paths individually? Well, I'm going to prove that by a double path induction. It's enough to consider that P is Reffel and Q is Reffel, and then Reffel.Reffel is Reffel, and so it has nowhere to go, so it's got to be Reffel. And we use this fact again, and then we're done. Okay, that's the argument. And so you can check that out for yourself. So the exercise is show that, and the one app_f P inverse is app_f P inverse. Oops, that's supposed to be -1 up here. And app_f P concatenate Q is app_f P concatenate app_f Q. You can do those as exercise. They're both simple path induction. Okay, so that's one aspect of functoriality which I wanted to get at. Every map respects path. And now notice there's going to be something cool that comes out of this. Let me refer you to a fact that something that we discussed before, which I'll bring us back around. This is really neat, okay? Watch this. Okay, here is like some simple thing you would like to know. If A1, let me think about this, yeah. If A1 equals A2 and B1, let's call it, equals B2, then you'd like to know, for example, that the pair A1, B1 is equal in A cross B to the pair A2, B2. It's an example of a congruence principle. Okay? You would like to know that, right? You would like to know that, remember, equality means path. So, but stated in the loosest possible way, I say if A1 is equal to A2 and B1 is equal to B2, then the pair A1, B1 is equal to the pair A2, B2. Why should that be true in a very offhand way? Well, the reason is let's put P here, let's put Q here, all right? And then what I want to do is I want to take the action on paths of the pairing constructor. So what I want to do is I want to say if I take app of app, if I curry pairing, call it pair, to P and to Q, that'll be a proof of that. Ta-da. So the congruence is expressed by the fact that every map, including the pairing map, has an action on path, where pair now here is being defined as, you know, the curried form of pairing. Okay? So I'm doing it like that. So this is just a quick sketch. Okay? All right. So that's one interesting fact. And now to discharge an obligation that I acquired for you before. So that's one. So the congruence property holds. The second thing is that this unicity property. So remember when we talked about pairing, we said if we have the Cartesian product, what happens is we have a map from here to here. These, in other words, this really means given Z in A cross B, second of Z is in B. Given Z in A cross B, first of Z is in A, right? We said if you have that scenario, and then we also said that if you give me any A and any B from gamma, then there's a map certainly here called pair AB. Gamma proves that pair AB is in A cross B, provided that A is in A with respect to gamma and B is in B with respect to gamma. So that's good. And the beta axiom holds. If you take the pair and do first, you get A, and if you take the pair and you do second, you get B. So these are definitional equivalences on these cells. And then the question was the unicity. Okay? So the unicity looks like this. The unicity says, I'll write it like this now. We're going to say, if I want to show uniqueness, I say, well, I have one map, call it pair AB. So what I'm doing is I'm zooming in. This business goes right in here, but I didn't have quite enough room. So what I'm going to do is, because I want the surrounding context to be the same. So I have one map, pair AB, which has the property that pair AB followed by second is B, and pair AB followed by first is A. Okay? So I have one map, and then to show unicity, I say, suppose you have any other map, call it C, which satisfies the same requirement. That if I do, so what I'm doing here, this is the zoom out, but I'll put it in here. I say consider two maps which satisfy the same conditions. That is, both of these satisfy definitionally those requirements. What I want to show is, in some sense, these two maps are equal. And the way we're going to do that is we're going to say one can be deformed into the other. So we're going to say that there's a cell here. Okay? And how do you do that? Well, the way you do that is you have an axiom. That's what really is going on here. And what the axiom says that C is deformable in A cross B to the pair first of C, second of C. And you should check that this gives us the unicity. So I claim if this holds, then you can fill this cell. Given this axiom, this cell can be filled. You can show how to prove that this is equal to that in the type A cross B. That's the unicity. So here is the condition. This is the universal condition for products. I talked about this, I think, in lecture 1. This is called the universal condition for products. Okay? So what it's saying is, so going back to a remark that Todd made, like possibly on day 1, is in a certain sense we're saying every element of the product is a pair, but it's not literally on the nose a pair. It can be correlated, it can be mapped. There's a path between it and a pair. And it's kind of a cheap way of forming a pair, because what you do is you say, I don't want to look at C. C could be, for all I know, is some process that when you kick it, with first or second answers appropriately. I don't know what it structurally is. But what I do know is I can turn it into the canonical form of that product type by a path which says I can deform C into this cheap thing that responds to first by saying first of C. It just hands it off. It's one level of indirection. And it responds to second by doing second of C. So it's one level of indirection. And now C can be thought of as a pair because I can put in a proxy object. So this is a proxy, right? So this is a proxy. All it does is the pair is the thing which, if you send it the first message, ask its first, this side, first, right, will just be the first of C. It just says, hey C, tell me your first and I'll pass that on to the guy who asked me. Okay? If you ask me for my second, I'll say, hey C, what is second? Oh, and I'll just pass that on to the guy who asked me. So it's a proxy. Okay? So, but it's deformable to such a proxy. It's not literally structurally a pair. So this is a remark I owed you from several lectures ago, so I wanted to get that in. Yep.
It's not clear to me why this has to be an axiom.
Yeah, well, it shouldn't be clear, but without it, there are various ways of defining the rules of a product in type theory, such that one way to do it, actually in the Hop book, it's defined a different way, and this ends up being a theorem. But then the other thing is an axiom. So it's a balloon squeezing exercise. So the way I did it, because I approached I noticed later that in the Hop book they treated, we ended up treating the product positively, but I wanted to treat it negatively. So if I treat it negatively, you do the way I said, and then you have this as an axiom. And the Hop book is treated positively, then this is a theorem, but then the pattern matching construct is an axiom. So, you can do it either way. Okay, so I just wanted to make that clear. So the idea is that it's this idea of a deformation of a two-cell, okay, that connects these things. That's what unicity, in my mind, should mean. Okay, it shouldn't mean that this is definitionally equal to AB. It should be that it is morally equal to the pair AB. Okay, that's the idea. Okay, you're going to do the derivation. Showing that this is equal to that, given that C satisfies these equations, is going to follow from this axiom, but you have to prove that. So that's an exercise. So exercises exhibit that cell, given this is an axiom. Okay, so you should be able to do that. Okay, I want to say another thing about functoriality, which is that about the issue of a fibration that we talked about before. So we're still in the business of saying, we're drawing out these. What I'm doing is I'm explaining the consequences of path induction, among which are the fact that everything in sight respects paths. So here's another sense in which we respect paths. So the idea is I want to be able to say, I want to say this. If F is a mapping from A to U, yes, it's a family of types like this, okay? Then I want to, I'm sorry, I need a path, and a path. I have a path in A. All right, well, let's just right now write it like this. So the rough idea is to say then, and now here's where the rub comes in. I want to say something about F of A should be in some sense equal to F of B. This question that I'm addressing right now is the heart of the whole matter of homotopy type theory because it gets to the idea of what is going to be called univalence. Okay? So we're gonna get to that in a minute. Okay. So what do we know here? So what do we know? So this is like informally like the idea. So what do we know? So in other words, I would like to say something like if A and B are equal elements of the domain of this family of types, then F of A and F of B should in some sense be the same type. So the motivating example we've had many times is we would like to say that because there is a proof that x plus y is in nat y plus x, I would like to know that vector of x plus y is in some sense equal to vector y plus x. Oops, I didn't, let me, we have to say in what sense do we have that. That's what we're shooting for. Remember that it's not true definitionally, right? Because this hypothesis is not true definitionally, so I can't get to any definitional equivalence because that's not true definitionally. Okay, so, but that's like the motivating idea, okay?
Sorry, you can tell me if this is something you're about to explain, but I think I see why this is true, but what's the exact reason why you can't just use the J rule for this, proving this by fiddling with universe levels and sort of...
Well, I think you're anticipating what I'm going to say. So how about if I just go on? Okay. So I'm pretty sure you're anticipating what I'm going to say. So let's do this. Okay. Okay. So here, all right. So you can see what we're doing here, right? Okay. Are you with me? Okay. All right. So that's the high-level thing that we want. And there's a question about what this even means. Okay. Here, because what does it mean for two types to be equal or interchangeable? So this motivates the idea of equivalence of types. That's where I'm going to get at. So what I want to get at is I want those types to be equivalent. And what does it mean for two types to be equivalent? So I'm going to introduce a notion, okay? So I'll define it like this. So I'll say, well, yes. All right, it's a little complicated to write out, so let me think about this. I'm running a little short on time, so I'm going to improvise a little bit. Okay, so let's say what I'm going to do is I want this to be, eventually, I want this to be f of a is equivalent to f of b. And what does that mean? It means that there's a function, let's call it little f, okay, from f of a to f of b, such that, okay, this thing is an equivalent. So what does that mean? Such that for every x in a, that this is an equivalent. Oh, take it back. Sorry, wrong about that. What I want to do is I want to say that there are now two things. Okay, so let me think about what I'm going to do here. Let's just write here now, is an equivalence f? What is an equivalence going to be? It's going to be a map that is invertible up to higher homotopy. That is, it's a function that has a pre and a post inverse, such that if I go from f over, if I go from left to right and then back by its post inverse, then I should get a homotopy. That is, we have this scenario. This should be this round trip thing, which I do here, like this. This composition should be the same as the identity. That is, there should be a higher cell, which is takes this proof and turns it into that one, okay? And conversely, okay? So whenever we have f going here, there's a g that goes back, and then their composition is the identity, and the other way around, I can go the other way around and get the identity. Okay, I'm having to sketch because I'm running low on time.
Does this have to be for index types, or does this work for arbitrary types?
It works for an arbitrary type. Okay, so there's a notion in general, this is an arbitrary type A, B, which in the case of interest here is f of A and f of B. Okay, so that's what I'm doing. So I want to have an equivalence between those two. The reason I want to have an equivalence between those two is because I want to be able to say, the way in which I'm going to say what this equivalence will mean then is if you give me something in this type, I can transport it over to this type and backward. So in other words, although the types vec of x plus y and vec of y plus x are not the same, they're equivalent in the sense that if you give me anything, if we take, as another example, if we take vec of x plus y over here, and we take vec of y plus x over here, we're going to say that those are equivalent. And what does it mean to say they're equivalent? It says, well, if you give me any vector v over here, I can send it to its analog v prime over here in such a way that if I send it back over here and I get, let's call it v double prime, let me make some more room. So if I take v and I send it over here to v prime, and then I take that guy and send it back to v double prime, there's a path between them. They're equal. Not identical, but there's a path between them. That's what the piece I erased is telling me. So what we're going to do is we're going to take a vector over here and we send it over here, and then when we send it back, what they're going to be is equal. Meaning they're going to have a path between them. That's weaker than saying it's exactly the same thing. So that's the notion of equivalence. So this is what I want to get to. So the way I'm going to get there is by the following route. Okay, so that's the plan, okay, via the following route. Now, someone mentioned to me, with a question that came up a minute ago, is notice, if we have a path between A equals B and A, then the action on paths of F by P is a proof that F of A is equal in U to F of B. That's automatic because the board, it's in the behind board or the erased board, the thing I just did about the action on paths. If we think of this merely as a function from A into U, it automatically has an action on paths, and it will take paths in the domain into paths in the codomain. That we know. But what I don't know is what's the relationship between paths in U and equivalences between types? Because equivalences will tell us that we can move things from one type to another. So the important thing about an equivalence, right, if I say A is equivalent to B, by definition, it means there exists an F from A to B that has some additional structure, which I'm writing as is-equiv, which means that it has a map backward that has the property that I've just described. So in other words, the equivalence of two types means we can transport one way, transport back in such a way that up to homotopy, those are mutually inverse things, so that they're interchangeable. Those types are interchangeable. So there's a, so this is we have as a fact, okay? So it can be, okay, sorry.
How is this notion different from isomorphism in category theory?
I can't hear you.
How is this notion different from isomorphisms in category theory?
It's the notion of equivalence in category theory is what I'm doing. There's a notion of equivalence of categories. And so what I'm doing is I'm saying the notion of is-equiv, when specialized to that setting, would be an equivalence of categories. Okay? If A and B were categories, F would be a functor. To be an equivalence is exactly to be that, because what you say is if you do F and then you do F inverse, you don't get the same object back, you get an isomorphic object back. Isomorphic here, so it's isomorphism up to isomorphism, and that's what I'm explaining here via the notion of path. So there's a chapter in the hot book about developing category theoretically on this kind of basis, and all of those things are made quite explicit. And so you can have a look there. Okay, so now let me get back to where I was. So let me look at the transport property. Okay, so that's just a remark. So right now, we're in the situation until I say something more. The thing I want to say to you is that this thing is not so far terribly useful to you. Because merely because